Last lecture, we used average velocity u in two different places. And the question that we should be asking now is, when is that a valid approximation, or is it accurate? And it turns out it sometimes is and sometimes isn't. Let's take a look at mass conservation first. The first time we used it was when we were assessing the integral for mass conservation. Mass conservation, the mass flow rate, kilograms per second, can be calculated based on this integral. The velocity times the density integrated over an area. This assumes that this velocity is perpendicular to the area. We said, okay, well, we didn't know that velocity specifically, but we substituted in an average velocity for that. And so the question that we're therefore asking here is, when is it true that the integral over that area of u rho dA is actually equal to the integral over that same area of some average velocity times rho times dA? So that's the question. In order to answer that question, we will look at the definition of u bar. So u bar's definition, or the definition of any average over an area, is the integral of that value over an area, integrated over the area, and then divided by the area itself. So that's simply a definition. And so in the case of these integrals, we can look at the situation if rho is constant. So if rho is constant, then we can pull rho out of those integrals. So we have, on the left-hand side, we would have rho, and of course u rho dA integrated over that area. And we would have on the right-hand side rho and then u bar dA here. Not rho twice, obviously. Rho dA, u dA, and u bar dA. So this one is looking, like this one. So we can take advantage of that. So let's do that. So we'll say, all right, this looks like that the integral of a u dA, 1 over a, is equal to u bar, which means the integral of u dA a is equal to simply a u bar. So that just comes from the definition of that comes from here, just the definition of the average velocity. So we can plug that in there, and so you have rho, and then we're saying that's equal to AU, is equal to AU. So that integral is equal to AU. And then the question is that the same as rho u bar dA? We can pull that u out because it's average, so it is actually constant. So rho a u bar, does that equal rho u bar integral of a dA? Well, it does, rho u bar a. So the condition for these two integrals to be identical is that rho is constant. True if rho is constant. So that's a pretty good approximation then, because we know that in a lot of flows, rho is constant. We're going to study a lot of incompressible flows. In some cases, of course, it's water, so it's truly an incompressible substance or some other liquid. And in other cases, it's simply a flow that is incompressible, because many flows are. And we'll talk about when that occurs later in the class. All right, so that's a good approximation if rho is constant for the mass flow calculation. But now we want to turn our attention to the momentum problem. And for the momentum problem, we have a different integral, although we substituted again. So the different integral we had for momentum was an area integral again. It was u rho, then u dotted with n hat. This is the u vector dA. And when does that integral, is it appropriate to substitute an average velocity in for that? So when does that equal, does this work for u bar? So the question then would be, all right, so we've got the integral a u rho u vector dot n hat dA. Does it equal the area of u bar rho u bar dA. And the first issue there clearly is this guy. We have to deal with the u vector dotted with n. The u vector dotted with n, in this particular problem, we can actually just take that dot product because we know that the outward unit normal was faced in the positive x direction. So if you recall, this was a nozzle problem, and there was velocity here, and that was aligned with the x-axis. So the n hat is just 1, 0, 0. So u dot n in this case is going to just be u. So this integral becomes u squared rho dA, and then the other integral remains u bar squared rho dA. So they look similar. We've got u here, we've got u squared here. Now note that u is generally not uniform, right? U usually in a lot of flowing through a surface, the velocity might be higher at the top, it might be higher in the middle, it might be higher at the bottom. It certainly does not have to be uniform. So this is varying a lot. The question is, when can you just replace that varying velocity with an average velocity and still have that work? So let's see if there is a condition where it can in fact work. All right, so that's the question still, and we can once again try to make use of the definition of the average velocity so we can compare the same thing to each other. So we have that. Now, this one, we can actually make some progress on this because if rho is constant, we can pull the rho out. And u bar is constant over the area because it's an average, so it doesn't change over the area. So that integral is equal to simply u bar squared rho times the integral of dA over A. So it's equal to, u bar squared rho A. So that has a very clear answer for this one. This one is average, which is why we did it, because we can actually take that integral. And the question is, when does this integral, therefore, equal that value? So when does this integral with a u in it, u squared rho dA integrated over A, when does that equal simply u squared rho A? Does it ever equal simply u squared rho A? Well, we can take, if rho is constant, we can take this integral and we can pull the rho out. So we have the integral over A of u squared dA. Does that equal u bar rho squared A? Right, so that's the question there, which means we can calculate what u bar squared equals in terms of that UA integral. So using the definition of u bar. So this one, u bar equals 1 over A integral over A u dA. So that's squared 1 over A integral A u dA. So we have two of those times rho times A. Does that equal this? Well, not really, right? So this is, we can take this, we can say, well, this is rho integral A u squared dA. Does that equal this? Well, that's 1 over A squared times A. So we got an A here. We've got a rho. And then we've got this integral A u dA squared. And those aren't the same. So this is, on the left-hand side, we've got rho A u squared dA. On the right side, we've got rho A integral A u dA squared. I'm sorry, this is 1 over A here. 1 over A. All right, so that's 1 over A. So these aren't the same. This is not an integral squared. It's a squared quantity, and then you take the integral of it. This is the integral squared. Those are definitely not the same thing. You can check that by trying some integrals and seeing. It definitely does not work. So no, these are not the same at all. So are they ever the same? And they are the same in one condition. and that's if U is uniform. If U is uniform, then this becomes constant, and we can pull it out of the integral as well. So on the left, we still have the integral of a u squared dA, but now we've said that u is constant. So that's the same as rho u squared dA. Well, rho u squared dA is simply rho u squared A. So that's that. And if you look back, the question was, does this integral equal u squared rho A for the u bar? And of course, if u is constant and uniform, then u bar equals u if uniform. So clearly, these are the same. So the condition for when you can use u bar instead of u in the momentum equation, you can use u bar instead of u in momentum if rho is constant and u is uniform. And of course, u is not usually uniform. U varies a lot. That's the whole point of fluid mechanics, is u is changing. But there are many flows where people treat u as if it's uniform to use calculations using the control volume type method. And we'll see, so we will see that as a very common technique, but it also is extremely important that you remember as engineers that that's an approximation. If you're doing a momentum analysis, or we'll see later an energy analysis, and you're assuming that these equations are working, they're assuming that u is approximately uniform, which it definitely may not be.